Hi everybody, it's Mrs. Smith again. So this will be the final video for Chapter 7, and this time we're tackling yields and limiting reactants. So let's get started. Alright, in the previous videos we have highlighted chemical change, and remember that's when a change occurs that alters the composition of the material, so what you start with is not what you end up with. These chemical changes are summarized quite nicely in chemical reactions or chemical equations. Those essentially serve as our chemical sentence, right? It tells you exactly what's reacting, exactly what's produced, and how much in terms of a molar ratio, and it can tell you the states of matter and all that too. So it's really succinct, but it's really powerful. And obviously you need a balanced chemical equation before you do any of the stoichiometric calculations that we've been learning about. So we've learned all that so far in Chapter 7. So now we're going to talk about kind of the products and then what you make in these reactions. And we're going to be referring to something called yield a lot. So yield is defined as the amount of product that is formed in a chemical reaction. So it's how much you can get out, potentially, how much you do get out, or perhaps the ratio of the two. So we'll talk about the three types of yield on the next slide. So when you start talking about how much product you can produce, there's a couple different ways that we can refer to these yields of chemical reactions. The first of which is the theoretical yield. So this is how much you are supposed to make in the reaction, right? It's if everything goes well, if everything works the way you think it's going to work, this is how much product you expect to get out of a particular reaction, and it is based on the stoichiometric calculations that you do beforehand. So essentially this is the perfect scenario. This is your perfect theoretical amount that you can get out. So whatever amount that you calculate, in terms of grams from your big stoichiometry calculations, that is the theoretical yield. The next step is the actual yield. So this is where real life comes in, right? So this is how much you actually get out. It's the amount of product that you recover in a chemical reaction. And by recover, I mean how much you have in hand at the end of the reaction. So again, a lot of things can happen. You can have potentially side reactions that make something that is still a product but is not the product that you care about. You could lose some stuff in purification. You could spill half of it. There's a lot of stuff that can happen. So this is actually what you have in hand at the end of the reaction. And that's why we call it the actual yield. And it's important to keep in mind that the actual yield is typically less than the theoretical yield just because life happens and stuff sometimes goes a little sideways, but it should never be more. And especially when you're in different lab settings, general or organic or higher levels of chemistry lab, sometimes you'll find that you'll weigh your stuff and you'll find, oh, okay, well, it looks like I have more product than I predicted I would make. That's weird. I'm in an undergraduate chemistry class. Did I just violate the law of conservation of mass? Well, no, you didn't. Usually it's that there's some extra water hanging around in that compound, especially if it's solids and it's South Carolina, so it's a little humid and stuff. So there's usually extra water hanging around. So if you take time to properly dry the material or do a couple different tricks, you'll get a mass that is lower than your theoretical yield. So just bear that in mind. Just because what you weigh immediately might be more, you didn't violate any massive laws of chemistry there. The final way that yields are sometimes referred to is the percent yield, which is the ratio of the amount of product that you actually recover compared to the theoretical yield or the expected yield. So the way that we calculate that is take the actual yield and divide it by the theoretical yield and then times it by 100 to make it a percent. So when you're doing this, again, just make sure that your yield quantities are in the same unit so that they'll cancel out, so you can have an actual ratio there. All right, so here's one that you can practice. It says nitrogen and oxygen react to form nitrous oxide, N2O, or we could call that dinitrogen monoxide. What is the percent yield if 10 grams of oxygen gas with this molar mass produce 21.8 grams of nitrous oxide with this molar mass? And are given this balanced chemical equation. So you're going to have to do a little stoichiometric calculations here and then try to find your percent yield. So go ahead and work through this, hit pause, see how you do, and then we'll talk through it together. All right, well, hope that went well. So we're going to talk through this guy together. So they give us here that we have 10 grams of oxygen gas, and then it tells us how much nitrous oxide, that we actually get out. So this here is our actual yield. So our job is to calculate the theoretical yield and then compare the two. So with our 10 grams of oxygen gas, we're going to use that and do stoichiometry to get from grams of oxygen gas to grams of nitrous oxide. So if you've forgotten from the last video, remember our flight plan is you take grams of A, in this case is the oxygen gas, convert it to moles using your molar mass, then go from moles of A to moles of B using the coefficients from our balanced chemical equation, and then go into grams of B or N2O using its molar mass. So I'm going to get started with the 10 grams of O2. So I'll put that here. And I'm going to convert grams to moles using the molar mass of O2, which they were kind enough to provide us. So 32 grams goes on the bottom, 1 mole goes on the top. Okay, so my grams of O2 cancel. Now I'm in moles. Now I need to use the coefficients from my balanced chemical equation to get my molar ratio. So for oxygen, there's no coefficient in front of O2, so that's implied there's just 1 mole of O2. And I have a 2 in front of my nitrous oxide, so that implies that I produce 2 moles of N2O. All right, so put the moles of O2 on the bottom to cancel with moles of O2 on the top. And now I need to go into grams of N2O by using the molar mass of N2O, which again, they were nice enough to give us. So it's 44 grams of N2O in 1 mole. Now please remember that the molar mass is always of just 1 mole. Doesn't matter what the coefficients are in the equation. Remember, this is true for N2O regardless of if it's in an equation or in a different equation or by itself. All right, so it's always the mass of 1 mole. So I can cross out my moles, leaving me in grams of N2O. So now we stop and solve. So I get that I have 27.5 grams of N2O that I could potentially make from my 10 grams of oxygen gas. So this is my theoretical yield. So now they asked me to find the percent yield. So I just take the actual yield, which is what they actually recovered, which happened to be 21.8 grams. That's what they gave me in the problem. And then divide that by my theoretical yield. And then I multiply it by 100 to make it a percent. So 21.8 divided by 27.5 times 100 would give you around 79.3% yield. All right, so not that bad. The only thing you have to recognize here is that since they give you kind of an amount that you collect, you have to remember that's the actual yield. And then since they give you one of the reactants, you have to calculate the theoretical yield and then compare them. All right, so thus far we have had some pretty idyllic chemical reactions. So far we've given you just enough of each that they both can react perfectly and be consumed and finished at the same time. But obviously, again, that's not real life. So in most cases, you're going to have one reactant that's going to be used up before the other. So we call that guy the limiting reactant. So it's the reactant that is used up or consumed first, and therefore it limits the amount of product that can be formed. So again, this one would be the first reactant to be completely consumed or completely used up, completely reacted. And then once that guy is done, there's no more reaction that can be had because you've lost one of your pieces. So the reaction stops when the limiting reactant is consumed. So the reactant that gives the smallest theoretical yield determines the theoretical yield. So again, the one that's used up first is going to dictate how much product that can be made. So the other guy that's present, or more than one guy, is called the excess reactant. So it's present in an extra amount. So essentially there's more of that reactant there than can actually react to form product. So essentially, once the limiting reactant is consumed, all the extra of the excess reactant will just sit there until you either add more of the other reactant or just collect it. So this is kind of challenging to think about in terms of chemical compounds, right? In terms of reactants and products. So let's look at, let's make hamburgers. So here we have, we've got hamburger patties, we've got buns, we've got cheese, and we've got, I guess that's tomatoes. You don't get any lettuce or ketchup or anything. Calm down. It's not that exciting. So here we're going to get just one of each of these things to make our burger. All right. So we have one patty, one bun, one piece of cheese, one tomato. So if we start to cross out the things that we can make, right? I'm going to use this patty, this bun, this cheese, this tomato. Okay, that makes one hamburger. Then I've got another patty, another bun, another piece of cheese, another tomato. That makes this guy. Then I make my third. I've got a burger, I've got a bun, I've got a piece of cheese, I've got a tomato, and that makes this guy. And then I go back to make another burger. Oh, what? I have no more burgers. All right. So I've ran out. So here, your patty would be your limiting reactant. You're going to run out of him first, and now you can't make any more burgers unless you can make this into some kind of weird grilled cheese thing, but it's no longer a burger. So here, again, our hamburger patties are our limiting reactant, and then everything that we have left over, so that would be, we have one hamburger bun, we have 1, 2, 3 pieces of cheese, and we have 4 slices of tomatoes. So, we have extra stuff that we can hang on to, and, those are our leftovers. We can use them later. They're still good, but we can't make any more burgers unless we add more hamburger patties. So that's all this is doing, but just kind of in a more user-friendly way. All right, in the next few slides, we're again just going to be looking at diagrams to kind of ease you into these chemical compounds. All right, so here we see our little diagram depictions with green spheres and red spheres, and we want to form the new substance that is the, compound with a green and a red sphere attached together. Here is how they were related in a chemical equation. Notice it's all a 1-to-1 molar ratio. So looking at, this is what you have, this is how many of each you have, I want you to look and consider which one is the limiting reactant, which one are you going to run out of first. So take a minute, look at it, see what you can figure out, and then we'll talk through it together. All right, so I know I need these guys to react together in a 1-to-1 mole ratio. So let's just count, see how many we have. For the green guys, we have 1, 2, 3, 4, 5, 6. So I have 6 of those. For the red guy, I have 1, 2, 3, 4. I only have 4 of those. So if we're trying to figure out how many of each of these we can make, all right, so we got to make the green-red hybrid here. So you can tell that since these are at a 1-to-1 mole ratio, you're going to run out of the red spheres first. So the red is going to be your limiting reactant. You can also kind of look at this picture and just try to circle. Okay, here's going to be 1 product. Here's 2, here's 3, here's 4. And I have the green guys left over. So again, I'm going to be limited by, I'm going to run out of my red guy first. All right, so here's another situation, but we don't quite have a 1-to-1 mole ratio here. So we've got dark purple and pink, and they're making this new substance here where it's got 2 dark purples to 1 pink. So looking here, counting what you have, tell me what's the limiting reactant. All right, so again, we've got to count. So with the dark purple, we have 1, 2, 3, 4, 5, 6. We've got 6 of those. With the pink, we have 1, 2, 3, 4 of those. All right. So before you answer it just like the first one, bear in mind here that we have a different reaction stoichiometry here. So here it takes 2 of the purples for every 1 of the pink to make your products. So really, you have to look at this in terms of the number of moles you have divided by the coefficient. So really, with the dark purple, I only have enough to make 3 of my products, as opposed to with the pink, I have a 1-to-1 mole ratio here, so I have enough to make 4. But again, if we were counting just like we did before, if I clear this out, if we're counting how many products we can make, you need 2 purple to a pink. So there's 1, 2 purple to a pink, 2 purple to a pink. And that leaves you with just 1 of the pink guys left over. And again, you consume the purple guy first. All right. So again, it's not merely as simple as just straight counting and comparing your numbers. You've got to pay attention to the reaction stoichiometry. All right, so now let's try it with actual compounds with molar masses and all of that. So methanol, CH3OH, can be produced by the reaction of carbon monoxide, CO, with hydrogen gas, H2, and it's provided by this balanced chemical equation here. If you have 365 grams of carbon monoxide at this molar mass and 65 grams of hydrogen gas with this molar mass, what is the limiting reactant? All right, so your choices here are either carbon monoxide or hydrogen gas. So see what you can do with this, see how it feels. Remember you've got to kind of look at, how many moles you have of each one and then compare the stoichiometry of them. So work through it, struggle with it a little bit, and then we'll work through it together. All right, so I had to switch over here just to give myself a little bit more room to write. So again, here we have 365 grams of carbon monoxide, 65 grams of diatomic hydrogen. Which one is the limiting reactant? So for each of these, the first thing you want to do is make them into moles. Again, to go from grams to moles, you just use the molar mass. So we have 365 grams of carbon monoxide, and we're going to divide that by the molar mass. So again, we put the grams of CO on the bottom and the 1 mole of CO on the top. Then we're going to stop here and solve. All right, so that's going to give us around 13 moles of carbon monoxide. I'm going to write the whole number out. So 13.0357 moles of CO. All right, I'm going to do the same thing for the diatomic hydrogen, 65 grams of H2 divided by 2 grams of H2 in every 1 mole. And that guy's going to be 32.5 moles of H2. Now, so before you get excited and see that CO is the smaller number of moles, so clearly it's going to be the limiting one, we first have to check the molar ratios. So here in the reaction, I'm going to be using 1 mole of CO for every 1 mole of methanol produced. All right. For diatomic hydrogen, I need 2 of these for every 1 mole of CO that I'm putting in. So to really check your number of moles, you want to divide by the coefficient. So here, obviously, we're dividing by 1 for the carbon monoxide, so that doesn't change. But for diatomic hydrogen, I'm going to be dividing by 2 because I need 2 of those. So that's going to be 16.25. All right, so here, once you divide by the coefficients, you get out these new numbers. Whichever one is smaller here is going to be your limiting reactant. So we looked out here, and carbon monoxide is actually still our limiting reactant, but it doesn't always work out like that. We're going to take these calculations a step further and calculate theoretical yield when you consider a limiting reactant. Please know that once you divide by the coefficients, you're going to never use those numbers again. You're going to use from that point on only the moles of your limiting reactant and go from there. But we'll see that in the next couple problems. All right, so we're going to take that same problem we just did. We have 365 grams of carbon monoxide, 65 grams of hydrogen gas. How many grams of methanol will be produced? So here this is, again, building off of our limiting reactant calculation. Since they give us amounts of two things, again, we can't just assume that they're both going to be consumed equally. So anytime you're given amounts of two of your reactants, you have to compare them and see which one you're going to run out of first, which is just what we did in the previous problem. So you convert both of these to moles and then divide by their respective coefficients. Whatever the smaller number is at the end of that is your limiting reactant. From there, you're going to only use the limiting reactant for your calculations. So in the previous case, we found that carbon monoxide is our limiting reactant. So we're going to go forward with all of our calculations with our limiting reactant, because again, he's what dictates the reaction. You're going to run out of him first, so he limits how much product you're going to make. So I said all that. So go ahead and try this, see how it feels. Just do your standard stoichiometry calculation with your limiting reactant and see where you get. All right, so again, I just need a little bit more room, so I flip to this blank slide here. All right, so again, we're going to base everything off of our limiting reactant, which in our case was carbon monoxide, because the numbers were all the same as the previous problem. So I'm just going to start from scratch. So I've got 365 grams of carbon monoxide. Since you've already calculated moles of carbon monoxide, you might have started there. And in either way, that's fine. So I'm going to again divide by my molar mass of carbon monoxide. And then in this case, I want to know how many grams of methanol I'm going to produce. So I look at my coefficients for carbon monoxide, which is 1 mole of CO, and my coefficient for methanol, which is, again, 1. So just a 1-to-1 correlation here. Then we go from moles of methanol into grams of methanol. So I put my grams of methanol up top and my 1 mole of methanol on the bottom. And again, the molar mass is always of 1 mole. So check to make sure everything cancels. I'm left in grams of methanol. So I'm going to stop here and solve. So after I do my math, I get 417.145 grams of methanol. Looking at what we were provided in the problem, I see that this needs to be rounded to 3 significant figures. So that would be 417 grams of methanol, which is letter C. So again, these are just standard stoichiometry calculations. I just went from grams of, in this case, carbon monoxide into moles of carbon monoxide into moles of methanol into grams of methanol. All right. So again, this is molar mass of A. This is your coefficients from your balanced chemical equation. And this is the molar mass of B. And if you had started directly from your mole calculations from the previous problem, you could have just started here and gone straight from moles of carbon monoxide to using the coefficients. So you can do it all again as I did here, or you can just pick up here and work your way to the end. Either way is fine. All right, further extending on this very same problem, we have the same amounts of CO and H2, but now we want to know the mass of excess reactant that are going to be left over after the reaction is complete. All right, so see what you can do about that. Struggle with it for a second, and then we'll work through it together. All right, so let's check this one out. So here I want to know the mass of excess reactant that are going to be left over at the end of the reaction. So we know that CO, or carbon monoxide, is our limiting reactant. So we're trying to figure out how much of our hydrogen gas, our excess reactant, are going to be remaining after all the CO is reacted, right? Because these just going to be extra. It's going to be left over. So again, we're going to do our standard stoichiometry calculation where we start with our limiting reactant. So again, we have our 365 grams of carbon monoxide. And again, I want to convert that to moles. Again, if you have that molar amount, you can just start here. I just forgot to write it down, so I'm just going to start from the beginning. And now we're going to go from moles of carbon monoxide into moles of hydrogen gas. All right, so we got to figure out how many grams of hydrogen gas we consume. So I have my 1 mole of CO from my coefficients and my 2 moles of H2, again from my coefficients. And then I'm going to see how many grams that is. So I'm going to use the molar mass. Make sure everything cancels, and then you're going to do your math to figure out how many grams of H2 you consume. All right, and I see that I have 52.1 roughly grams of hydrogen gas consumed. So that's how much is used up in the reaction. Please notice that this answer will always be a choice if it's multiple choice. So just because you see an answer that you get, don't get too excited. Make sure you're answering the actual problem. So this is how much you use up, but you've got to see how much is left over. So to do that, we're just going to subtract what we started with what we used up in the reaction. All right, so we just take how much we started with, which is 65.0 grams, minus how much we consumed, which is 52.1429 grams. So we're going to subtract those two and see how much we have left over. So I get about 12.8571 grams of hydrogen gas remaining. If I do look at my sig figs, or in this case decimal places, I have 1 place here, 4 places here, so I'm going to round this to 1 decimal place. So that's going to be 12.9 roughly grams of H2 remain, which is letter C. So it's that one extra step. If you're looking for how much is left over, you've got to calculate how much you use using stoichiometry and then subtract what you started with minus what you used. So not that hard, but just requires an extra little step. All right, the final few slides are, again, just practice for you, just going through the exact same problems that we went through step by step. So here you've got aluminum sulfide and water reacting to make aluminum hydroxide and dihydrogen sulfide, which is actually a pretty toxic gas. So we want to know which reactant is in excess, and more importantly, what is the limiting reactant. You're going to use this limiting reactant calculation to figure out how many grams of the excess reactant will remain. Whichever one's limiting, you're going to calculate how much of the other one you have left over. And then how many grams of H2S you will produce. All right, so those are 3 great problems you can run through on your own. The answers are on the next slide, and I'm going to be doing my work on this slide. So again, I encourage you to kind of stop the video, try to work through these on your own. Don't look at the answers yet, and see how you feel and kind of figure out where you might need some help. All right, so the first question asks which is excess and which is the limiting reactant. So again, we've got to take our 15 grams of Al2S3 and our 20 grams of H2O. And we've got to first convert these guys to moles. Now, they don't give us the molar masses for these, so we have to calculate these ourselves. So for aluminum sulfide, we have about 150.17 grams in 1 mole. Again, putting grams on the bottom to cancel with grams on the top. For water, it's about 18 grams of H2O in 1 mole. Grams on the bottom to cancel with grams on the top. So now we have to divide and to get our number of moles of each of these. All right, so we get about 0.09 moles of aluminum sulfide and 1.11 moles of water. Now again, before you make your assumptions and pick your limiting reactant, we've got to make sure that we divide these by our coefficients. So for aluminum sulfide, we just get essentially the same number. And for water, we have to divide that by 6 because of the coefficient here. So we divide water by 6 and we get 0.185. So again, still here, the smaller one at first is still our limiting reactant, but again, that's not always going to be the case. So just double check that. So here our limiting reactant is going to be aluminum sulfide, and that means water is our excess reactant. All right, so that is number 1. Got that done. So Al2S3 is limiting, H2O is excess. So next step is to figure out how many grams of the excess reactant will remain. Again, we've established that that's water, so how much do we have left over? So again, you've got to start with your limiting reactant, which is the 15 grams of the aluminum sulfide. Again, you can start with the moles that you just calculated. I'm just going to go the whole way just so we get practice. All right, so again, we convert it to moles first. Then we go from moles of aluminum sulfide, using the balanced equation, the coefficients from there, into moles of water, which is our excess reactant, so 6 moles of water. And then we transfer that into grams of water. So in 1 mole, we have 18 grams of H2O. Double check and make sure everything cancels the way it should. And we are going to stop and solve here. So we get about that we have 10.8 grams of water consumed in this reaction. So again, we've got to know, or it asked, how much water we have left over. So we take the 20 grams that we started with, that they gave us in the problem, and subtract from it the amount of water that we used up, which is at 10.8 grams. So that we get that we have 9.212 grams of water. Based on our subtraction rules, that would round to 9.2 grams of water we have remaining. All right, so don't forget that extra subtraction step when you are trying to calculate excess reactant left over at the end of the reaction. The final question asks how many grams of hydrogen sulfide will be produced. So this again is just a straightforward stoichiometry calculation. You just have to start with your limiting reactant, which again is that 15 grams of Al2S3. Again, converting it to moles. Again, if you just saved the mole amount, just use that. And you can save yourself a step because we keep doing the same grams to mole calculation each and every time. All right, so then we go from moles of aluminum sulfide to moles of dihydrogen sulfide or hydrogen sulfide. So the coefficient in front of Al2S3 is 1. The coefficient in front of H2S is 3. Then our next step is we have to convert from moles of H2S into grams of H2S. So the molar mass of H2S would be around 34.07 grams of H2S in 1 mole of H2S. Again, double check, everything cancels as it should. I wrote H2O here, but clearly I mean H2S. And then you just stop and solve. So if we round to 3 significant figures, as what we're provided in the question suggests that we do, we get about 10.2 grams of H2S produced from this reaction. All right, so again, not challenging, just builds on skills that you already have. The only thing that you have to add in here is that you have to calculate for your limiting reactant and then use that each and every time you're trying to figure out any quantities. All right, so here as well, we've got another practice problem. So we've got platinum metal, 30 grams, reacts with an excess of hydrochloric acid HCl, and chlorine, 50 grams, to form chloroplatinic acid, H2PtCl6. So we have our standard questions: what's excess and what's limiting reactant? How many grams of the excess reactants will remain after the reaction? And how many grams of the product can you produce? So I will argue that this question is written a little bit confusingly. It's unclear where it says reacts with an excess of HCl and chlorine, if it means that both chlorine and hydrochloric acid are excess, or if just the HCl is excess. So I would not make any assumptions, and since they give me gram amounts of chlorine and gram amounts of platinum metal, I would do my limiting reactant calculations with both of those. So again, hit pause, work through it. Same exact steps as you did last time, except for this time you have 3 reactants, although that's not going to make this problem any longer because they don't give you a precise amount of hydrochloric acid. So you're only worried about, if platinum's the limiting, how much chlorine you have left over, or if chlorine's limiting, how much platinum you have left over. So again, work through it, hit pause, and then we'll solve it together. All right, so again, I'm just going to go problem by problem. I needed a little extra room, so we're just going to work through them just like I did on the last problem. So the first thing, again, you've got to figure out is which one is your limiting reactant. So you have platinum metal. So we're going to start with our 30 grams of platinum metal. And we have 50 grams of Cl2, of our chlorine gas. And again, it tells us we have excess HCl, so we're not worried about that one. So you have to first convert both of these to moles, so we'll do that now. All right, so we convert them both to moles by dividing by their molar masses. And again, our final check here is to divide by these coefficients in the balanced chemical equation. Whichever one turns out to be smaller is your limiting reactant. All right, so again, the platinum moles just stay the same. The chlorine moles get reduced by 2. So that is 0.352 and some change. So again, we find that what was the smaller number of moles at the start is the smaller number of moles at the end. I keep telling you it doesn't always work out that way. So you're just going to have to believe me, since every problem that we've run through works out that way. But always just double check just to make sure. It's not tied with the grams. It's not tied with the moles. It's tied with the moles compared to how many is needed in the chemical equation. So platinum in this case is our limiting reactant, which is good because platinum is really expensive. So you definitely don't want to use an excess of platinum just because it's really expensive. So I'll put Lr next to platinum for a limiting reactant. And I'm going to remember this number of moles here so I can shorten my calculations. So 1538 moles of platinum. So when I do my next calculations, I can just skip that initial grams to mole step. All right, next up we want to know how many grams of excess reactant we have remaining. In this case, we're only going to worry about the chlorine because it gives us the actual chlorine amount. They don't tell us anything about HCl. So we're going to start with the number of moles of platinum. And then I'm going to go from moles of platinum into moles of chlorine. Again, using my coefficients. So every 1 mole of platinum, I consume 2 moles of chlorine. And then I go from moles of chlorine into grams of chlorine using the molar mass of chlorine. Make sure everybody cancels. And now I have to stop and solve. So I find that I have 21.8 roughly grams of chlorine consumed. Always a good check is to make sure that this number is less than the number of grams that you started with, because if it's not, you probably calculated your limiting reactant incorrectly. So here we have 50 grams of chlorine that we started with. We're going to subtract from it the amount of chlorine that we consumed. and get how many grams of chlorine are left over at the end of the reaction. So 50 minus 21.8 and some change gives us 21.1912 grams of chlorine remaining. We're going to round this to 1 decimal place. This becomes 28.2 grams of Cl2 remaining at the end of the reaction. And last but certainly not least, I want to know how many grams of my product, the chloroplatinic acid, I can actually produce. So again, I'm going to start with my grams of, or not grams, this time I'm starting with moles of platinum, just to save myself a step. Again, if you wanted to go back to grams, that's fine as well. Then we're going to look at our mole to mole ratio. So for every 1 mole of platinum I put in, I get 1 mole of my H2 PtCl6 out. So my moles of platinum will cancel. Then I go to grams of my chloroplatinic acid. So for every 1 mole of H2 PtCl6, so 1 mole of that guy weighs 409.796 grams, so he's a real big guy. So now we just take our number of moles, which is 0.1538, times our molar mass to get that we have 63.0266 grams of chloroplatinic acid, rounding it to 3 significant figures. That's 63 grams of chloroplatinic acid even. So again, these aren't super scary. It just builds on skills you already have. The only new thing we've learned is how to find the limiting reactant. And then obviously if you're going through the trouble to find the limiting reactant, you definitely want to use that in all of your subsequent calculations. So hope this video helps. You can kind of dive into the math and work through the practice problems. And as always, reach out if you have any questions. Thanks, guys.